Our next speaker is Yoshito Otake from the Nara Institute of Science and Technology in Japan. Some of you may remember that some time ago we had the visit of Yoshinobu Sato. He's from the same lab in Nara. Professor Otake has been working in this lab for some time. Before he was in Johns Hopkins University. And, well, also I will ask you actually to introduce your, your story first. And I would like to give word to you, please.
Thank you very much. Well, so I really appreciate Miguel to give me such a great opportunity. I mean, it's so great that it makes me nervous because big, you know, I mean big, in between big professors. And so please get relaxed. My talk is gonna be short. Like a coffee break. So, okay. Yeah, Yoshinobu Sato, he came here. So I've been working with him for 4 years at Nara. Before that, I was at Johns Hopkins University, which I still have some collaboration. Okay, that's just my introduction, brief introduction, and I'm going to talk about my research. So I'm going to talk about only muscle analysis, very specific topic. I'm interested in skeletal muscle, especially not heart muscle, skeletal muscle. And this project is a collaboration between many different countries and different disciplines. For example, those guys are specialized in tractography. These are biomechanics specialists. These are orthopedic surgeons. They are anatomy, Department of Anatomy in Korea. So just a brief introduction about our research institute. Our university, actually. I believe you all know where Japan is. So I didn't put the world map, but in Japan, we are located here near Kyoto and Osaka. It's a very historical city. Actually, it was the old capital in Japan, so there are many old things, temples and stuff. If you are interested in, if you have chance to visit Japan, let me know. I can give a good tour. So this is my acknowledgement slide. Yoshinobu Sato, my advisor. And Yuta, he's here at the middle. So he's doing a great job in deep learning in our lab. And other people, I really appreciate this interdisciplinary collaboration, international collaboration. So, okay, let me start. Background. So I'm interested in, as I said, muscle modeling. So in biomechanical simulation, for example, that's one main application target area. So for especially orthopedic surgery, planning of orthopedic surgery and rehabilitation medicine. That's our main target. So classically, these string-typed muscle models, these from Dr. Scott Delp's group, they developed an open source platform to perform simulation, which is called OpenSim. Anybody, this is commercial software. This is one of my old work that employed this simplified muscle model. Just, you know, this simplifies the behavior of muscle as a few string. But as you can imagine, this is not enough to well, this works pretty well, but we can do better if we have something more, realistic, volumetric model. So a quick recap about skeletal muscle. Well, skeletal muscle is the power source of motion, which originated from fiber contraction of each fiber. And the important functionality is, of course, transmitting the force. So the important aspect is the attachment area where this muscle attaches to the bone. That's what we want to know as precisely as possible. So, well, this kind of just this muscle shape is not enough. We want to know this attachment and directionality, specifically the muscle fiber structure. That's we want to model patient specifically. And one thing we noticed is the clinical CT with, obtained in routine clinical practice. It has information about this fiber structure. This is each slice, which is very noisy. But if we extract one muscle, this is gluteus maximus muscle, hip muscle. So, and then if we project, if we create the DRL, we can see, sort of this directionality. This is fat tissue in between the muscle tissue. So lower X-ray attenuation than the muscle tissue. So we can sort of see, we can have the information from clinical CT. And clinical CT is everywhere, especially in orthopedic surgery. This number is very small compared to your database, but for us, this is huge, large scale, actually. Well, this is specific cohort, THA surgery. So Japanese, relatively old women cohort. So this is very hard to collect, actually. 1,000 CT we have, so we can sort of do the population analysis. So first, muscle shape. This is a neural network. Well, we don't do so complicated thing. We just apply unit. Well, Yuta applied unit to 20. So training data set is 20 CTs annotated by orthopedic surgeons like this. We segment into 19 different muscles. And this is one typical example. This is an expert trace, the ground truth. And unit does pretty good job. This is dice coefficient and surface error. So we have previous classic approaches, that not classic, but one generation before. This is called multi-atlas method. And unit does really amazing job. And it is quite fast, of course. So we can do sort of population analysis like this, and we can, for example, find like this diseased or imbalanced patient. So the surgeon's focus is the balance between the muscles. If some patients have larger muscles in anterior portion, some patient has different balance. So that changes rehabilitation plan, for example, and surgical plan, and so on. One thing we have done here is to measure muscle force physically, and we analyzed the correlation between muscle volume and muscle force, which correlates pretty well. And the next topic here is the analysis of attachment areas, this part. This is very hard to estimate from image, actually, as you can imagine. Image does not provide information of physical attachment. So what we have done is physical measurement from, in this case, 20 cadaver specimens. We went to United States, and these orthopedic surgeons dissected each muscle physically and measured the attachment area. This attachment area varies, actually, has variation among subjects. So that's what we wanted to model. So this is one work that Dr. Fukuda has done, Mr. Fukuda. So he created the statistical model of the attachment area. This red area is high probability of being inside the attachment among 20 subjects. We have done different muscle attachment areas and created sort of statistical model. And then what we did is to estimate this muscle fiber structure based on the knowledge of shape and the attachment area. So this is one database we use, which is called Visible Korean Human Data Set. Maybe some of you may know. This data set is a very high resolution RGB image. So they freeze cadaver body and physically cut at 0.1 millimeter interval, and they took photos, very high resolution, well calibrated photos. So this is a great data set for us, the gold standard data set that we can compare. So they have also CT data set of the same cadaver specimen, so we can sort of evaluate our algorithm using the ground truth RGB image. So this is just a bit detail of the database. You can, if you are interested in, you can search this paper. They have this RGB image, and also they provide segmentation mask. And they have 3 subjects, actually. So 1 male data set and 2 female data set. So this is our ground truth data set. So regarding muscle fiber analysis, so classically, this is a conventional approach. So if you want to know, muscle fiber arrangement in 3D, there's no way. There's really not quite easy. It's not easy. One group did a rabbit study. This is, they fix a rabbit specimen and they peeled each fiber one by one, and 3D digitizer, they recorded the 3D trajectory by digitizer. Or this work is human study, and they just measured the surface fiber from just visible observation. But the limitations are quite clear. It's not it's destructive measurement, so it's not easy to measure intact 3D body. And there are medical imaging modalities that provides muscle fiber. Of course, ultrasound you can do, you can see this orientation, or diffusion tensor MRI, or micro CT. Those are conventional, not so old, but previous studies. But as I said, CT, clinical CT is everywhere. It's very, very convenient. So what we are trying to do is to use clinical CT using this template. So our strategy is pretty straightforward. We create a good, accurate template from this high-resolution image, and then just register the template to each patient. So this is how we compute local orientation from CT. This is classic image processing called structure tensor. We just compute this tensor representing orientation at each voxel. And then, so here we compare tensor field, the orientation derived from optical image and CT image. So just we wanted to see how they align correctly. And from CT image, those are different patient, clinical CTs. We actually can extract those local orientations. So this is one Mikai paper last year, which creates this kind of template. Well, in this paper, we described how to create the template from high-resolution data. This is the result. We have, in this case, two subjects, the same muscle, but you can see different shape and alignment of the fibers. So as I said, our strategy is just to register this template to each CT. It's a bit hot. Can I drink water? So this is our Mikai paper this year. So, sorry, just a bit cluttered slide. But basically, we just proposed one cost function that includes both surface area, surface distance, and vector field difference. So those two cost function, two terms plus smoothness penalty. So this is our cost function that we minimize. We use this CMA-ES optimization, and it needs about 600 seconds on the GPU. So this is how we evaluate this method. We create a template from one subject and register to CT and MRI of the other subject, and then compare with the ground truth optical image derived template of this subject. So this is our answer, and this is our estimation. So just to visually compare, this is estimated from CT, and this is estimated from optical image. So we can see sort of well-aligned muscle fiber structures. And this is a quantitative evaluation result. So our error metric is called fiber distance error. This is a sort of standard in tractography literature. So this computes average distance between two fibers, two curves. If you look at the estimation from CT, we can see sort of error here. And if we use MRI, this is much better. The MRI has much larger, higher contrast. So it provides better fiber arrangement. And these are previous method. So one paper, this paper, used, for example, computational fluid dynamics approach. They simulate water flow from here to here. But this provides bad estimate. And some other muscles. This is gluteus maximus and minimus, and we can do the same thing from clinical CT. And this is just a bit extra analysis. We can sort of balance between surface shape and the vector field alignment. This parameter changes the balance. For example, if we rely only on the surface, we get something like this. But if we rely on vector field as well, we can get a better fiber field. A few more slides only, sorry. Okay, so we are trying to extend this to other muscles like this, and hip or in head muscle. We also have collaboration with dentists who is interested in mastication. So this is one of our interests. And also, this is another Mikkai paper. I just wanted to mention this paper because I like this work a lot. This is image synthesis. Maybe many of you knows this GAN, the generative adversarial network, and also maybe cycle GAN. So this creates CT image from MR or vice versa. That's amazing, just surprising. I don't know how it works, but yeah, the more surprising thing is we don't need paired database. We just, so classic method, we need the CT and MR from the same patient of the same posture. But in this method, we don't need that. We just need a lot of MR and a lot of CT, put it in the GAN or something, and then it creates a beautiful CT image like this. For example, this is our real input MRI. This is synthesized CT. And we have, for example, a segmentation, a training data set on CT. So we are good at segmenting CT. That's why we create CT from MR and then do the segmentation. Just the last two slides. This is just a future, maybe not, I don't know how much we do along this line, but of course, AI is one direction, deep learning, great. But we are also interested in more like statistical modeling. Maybe because we have limited training data set. So one thing we can do is classic PCA-based statistical model using these fiber structures. So, for example, this is the first mode, the first principal mode of this muscle fiber structure. So, well, this is one future work. And yes, this concludes this talk. Thank you. Thank you very much.
Any questions?
Thank you very much for the talk. It's a curiosity. I don't know if it makes sense. But in order to improve your training data sets, to improve the number of data sets, would it be possible then to take the limited number of digital image acquisition you have with the Korean visual human and then morph the fiber structures that you have onto CTs so that you generate kind of synthetic database that shouldn't be too off for normal muscles, and then you can use it?
Yeah. Many people use GAN, image synthesis method, for augmenting training data set. So yes, I think that's great. We can generate more high resolution volume, RGB volume. Yes, I think that's one great direction. Thank you.
Any more questions?
Great talk, thank you very much. When you used MR, did you use also diffusion tensor imaging or just anatomic imaging? Would that be possible even? Or is the resolution not good enough?
So the problem of diffusion tensor in muscle, skeletal muscle, is motion artifact. They do small muscle, specific area, but we can't have the entire tensor, diffusion tensor image. So that's one limitation. But I think we do need, as a ground truth, so sort of one reliable truth. We can have one specific muscle. That's what our future project.
Thank you.
Okay, so in the last case, I'm wondering to know how you validate the synthetic images that you generate from the MRI, how you validate the convergence of the network in this case.
Validation.
Yeah, validation is very important in GANs, and especially in this case.
Answer, Yuta?
Yes.
Well, this is always the question, yes.
Yeah.
But I think we do indirect evaluation.
I think that you need to validate the distribution of the data, of the generated data, because it is very difficult to know if this case is coming from the MRI that you put in the input.
Do you have a solution?
But it's quite related to what Jordina is implying. I wasn't aware until recently of this use of these techniques to synthesize CT images from MR, which I find super, super interesting, and a lot of clinical applications. But then what I didn't expect it is not to take into account the physics of the generation of these images. It just, let's do the magic for deep learning and forget everything we know about how these images are built. And I don't understand. I mean, because the physics, we know the physics, right? I mean, for MR and for CT. And all this information is neglected. Like, well, let's do the magic. And it just, again, this becoming agnostic to data, agnostic to physics, and just run the algorithm. And I'm pretty sure that this information could help when combined with this, obviously. So I don't know which are your comments about it.
Well, so I saw one interesting Mikai paper this year. So they use GANs, but they check, if you don't have two more, for example, in training data set, and if you want to test two more patients, what happens? Or if you put 10% two more patients in training, what happens? That was interesting paper. I have no answer. Yes, I agree we need to consider physics, definitely. But this is, I think, one way of, so data harmonization is one, I think, keyword in this area. In this case, we just want to do segmentation. That's our task. This is just one representation to achieve this goal. What is your answer, Professor?
Well, I agree with Oscar that you completely ignore. Yeah, it's rare to say that, but it's that you don't really take the physics into account. But I guess, like you say, your only purpose is to produce a segmentation, correct? You don't really care whether the actual CT image really respects the physics, because what you really should validate is whether the segmentation is correct, not whether necessarily the intermediate result might be correct.
I think so, yes.
So actually, to continue a bit on this, in fact, this was one of the big debates a bit in MICA. Yeah? There were a number of papers generating images, like generating PET from CT. I mean, you take a PET because you can't see in CT what you have to see, right? So you're kind of making up information, right? And unless this is really, this has a solid explanation, like you say, in terms of physics and things, it will create beautiful images, but and this is a bit of a debate that we had sometimes about your work in image reconstruction and things, because in fact, yeah, it's something, parallel imaging has been around for a while, and you can reconstruct from sparse and little information, but there's a theory behind it. The data is there, yeah, you just have to treat it. But once you go to the extreme of getting very little data and generate images or do things like this, it's quite controversial. So. But if there are no further questions, I would like to thank again.
Thank you very much.
Okay. So our last speaker, and by no means least speaker, is Julia Schnabel. Okay, so our last speaker is Julia Schnabel from King's College London. We also know Julia for a while. In fact, Julia was here just a week ago. She was very kind to come and examine the thesis of Walid. And right afterwards, she went to Mikai and came back again here. And actually, before the thesis of Walid, she came directly from the States. So you probably are very much looking forward to going back home at some point. So very much thank you for taking the time to come here.
Okay.
Please go ahead with your presentation and also your introduction.
Okay. I wanted to start. It feels like I've only been here last week, which is actually true. So it's a bit of a déjà vu for some of you. Okay, my introduction. So I did my PhD at UCL, coming from Germany. And in medical image computing already, and then I moved to Utrecht in the Netherlands for 1 year, where I mainly learned Dutch, not much else. And I made a lot of great friends though, which I still meet at MICA every year. And then I went back to London, to Guy's Hospital, which has just become King's College. It was just submerged by King's College London, where I met Oscar, in fact, and he's written some landmark papers with my very humble support at the time. And we both then moved to UCL together. If I have to do a mental reconstruction here, very sparse, it's very undersampled. We founded together with David Hawkes the Center for Medical Image Computing, CMIC, which after I left became really big. moved up in rankings, and I moved to Oxford, which went down in rankings the same year, so that tells you something. So in Oxford I had my first academic post, worked a lot with Mike Brady at the time, for those of you who know him. And then after 7 years or so of commuting between London and Oxford, because I still lived in London, I got kind of called back and went full circle to King's College. So it was quite nice to be there, and I've been there for 3 years now. And 4 years ago, for some weird reason, I agreed to help with MICA and become program chair, and that's why I'm slightly exhausted this week, but everything's fine. I'm very mellow and relaxed, and I'm going to show you some of the highlights we've done recently on deep learning for image quality control. It's linking quite nicely back to Daniel's talk, and in fact, a lot of the research is in collaboration with Daniel and his group. Also, I'm looking a little bit at what I call attention maps, but there are different names for that. It's basically looking a little bit under the hood of the deep learning networks in fetal imaging. Again, it's a collaboration with Imperial, with Daniel's group and colleagues. Right, so there are two parts of this talk, and I promise it's only 30 slides. Now it's only 29 slides. And I realize I've got the graveyard slot here, and you'll be all very tired and fed up, especially if you've been at MICA all week and had a lot of talks already. So I'll be talking a little bit about the large image databases, UK Biobank, which we've been using here as well, where we want to detect image artifacts. So we want to basically sort out the good from the bad. And because Oscar mentioned that before, UK Biobank is such a nice, tightly controlled system, it doesn't really reflect what's going on with what I call our data in the wild in our hospitals. So we have what's called a class imbalance problem. We've got really nice data sets. But it helps us in training good data, but it also means we need to simulate bad data, which Siemens found very ironic when I mentioned to them after they've spent so much time getting really nice imaging protocols, and I just degraded radically down. But then we also said, well, okay, we're not only making image data look really, really bad, we also want to actually make bad data look really, really good. So we try to go both ways here. And then fetal ultrasound, I'll just give you little snapshots of what we're doing, where we use deep learning. Everything uses deep learning here, almost, for organ detection, where you can, and Daniel has shown one example already, and I'll take it a little bit further. And we also have something new, which is registration. So image registration isn't quite dead yet, but it's sort of a bit on ice right now. But people are starting to work again on image registration recently using deep learning. We try our bit there as well. And then also we're looking at increasing the field of view of ultrasound images, because the probe only has a very narrow angle sometimes. And then we also do a little bit of surface reconstruction in real time from ultrasound. So there are good and bad images, the good, the bad, and the really ugly, I guess. So here's some examples of good abdominal CT and bad abdominal CT, cardiac MR, which I'll be talking about, echocardiography, which is the case, that's why they don't use it in biobank. It's very operator dependent. It's very dependent on the probe which you use, on the experience of the operator, and then of course on the patient as well. So there's lots of different things coming together there. So we look at MR because it's beautiful and we like it. But if you've got bad images, any subsequent processing, any extraction of what could be clinically meaningful information could be compromised by the poor quality. You want to maybe segment organs, you want to extract the ejection fraction, quantify some other form of function, and that might be just not very good then. So for large population database, we've got, in principle, we will have access to 100,000 different cases. Those are not patients, but they're also not necessarily healthy. That's actually important to know. This is a cross-population study. So these could be people who have heart problems, who have diabetes, who have dementia and other forms, just as you would expect in a normal population, in a fairly normal population. They will be probably slightly healthier on average, because very sick people wouldn't volunteer to participate in that, but a lot of people actually have problems they didn't know. And it's quite interesting to like start thinking about links of cardiovascular disease and liver disease or things like that. Yeah, but it's generally good quality data, but our hospitals have more quality control issues. Our patients, they can't hold their breaths very well. They have arrhythmia, they have other problems, which then compromises the image acquisition. So I'm going to focus on two things here, on what's called off-axis for chamber views of the heart. You can see that, maybe it's a pointer even here, if I'm lucky. No, it's not. It's just everything lights up, but not the pointer. That would push any buttons. So you see like a nice four-chamber view on the top left, which is a good planning scan, and then you see one which is a bad planning scan because you see the aorta coming through. So it's a so-called five-chamber look. Of course, you don't have 5 chambers. This is kind of a bad acquisition. And then there are motion-related issues. Where would I press then? Above the one. Ooh. Ah, okay, thanks. So you've got motion-related issues. So this is like a good quality scan, and this is a motion artifact of some sort. It could be due just simply to breathing. So they could have this slice effect, which Daniel has shown before. I mean, the heart is moving in and out of plane, so things might be just some spatial blurring. But what's probably more likely that it's mistriggering, that the ECG gating didn't work quite well, so you're actually mixing different phases of the heart when you reconstruct the images, and I'll show you that in a bit more detail. Or it could be arrhythmia, and of course that's quite common in cardiac patients. Other artifacts would include, and then you allude to the interslice motion, the respiratory motion, or incomplete heart coverage if you want to calculate the ejection fraction and you haven't fully covered the heart. These are things that Daniel's postdocs are working on, and I'm not mentioning them here. So I'm mentioning on the first one, I focus on the first one, the correct four-chamber view planning. If you want to do that, you have to take before you take the four-chamber view, you have to do 2 more planning scans. You take a 2-chamber view and a short axis scan, and then you place an angle on both of these scans, and after that you know actually where to take the 4-chamber view from. And it needs to exclude the aorta. If you don't do that, you get this 5-chamber look. Yeah? And it's basically because the presence of the left ventricular outflow tract or the LVOT. And that, if you want to do subsequent atrial analysis, could lead to problems. So the idea here is that if we've got a large database, we want to detect these cases. We want to say this is not a good data set, you can't use it. The ultimate idea, the next idea would be to detect it while scanning the patient and actually say, oh, let's repeat the scan straight away. And the next idea would then be far in the future that we actually detect it in a way that we can solve it without actually having to do much. I don't have to recall the patient, we just resolve it in case-based maybe. So this is just the first step that we detected. And we do a very, very simple CNN approach. This is the work by my postdoc Ilkay Oxus. Was presented at ISBE earlier this year, where he does just some extraction quickly of the heart from the 4-chamber views. So it's a 2D approach, just taking the 4-chamber cardiac MR, doing a bit of template matching, extracting a square region of interest, throwing it into a simple neural network, and basically the output would be either 0 or 1. Is LVOT present or not, or the other way around? So if it's 0, it's a good quality image, the LVOT is not present. If it's 1, it's a bad quality image, and the LVOT is present. So it's a very simple binary classification. We do some data augmentation. We rotate and translate to create a bit more data. And everything else is really, really simple. Yeah, we did not try to be clever here at all. And because it's such nice controlled data, we looked at, I think, in our data set, we've got access to about 3,600 scans at the moment. And we found 123 which had LVOT present, which is tiny. In a normal hospital setting, you would have much more. Yeah? So we said, oh, well, let's just, all right, randomly pick 123 good quality images, make it a balanced class problem, extract several temporal frames of each sequence, so we get then 615 images for each class. And then we did, so it's very, very low numbers of data sets we're actually working. This is not really big data. And then we did stratified tenfold cross-validation. We compared this approach, so a simple classification, LVOT present or not, against standard machine learning classification methods, because I always say you have to do the baseline comparison, not just throw in CNN and report the result. You want to know actually what else could have been. And it turns out that actually linear SVM is not a bad tool. We all know that. We've been using SVM, well, not the youngsters amongst you, but we've been using it for the past 15 years at least, quite regularly. But if we do CNN, we do see quite an improvement in accuracy from maybe 73%, probably the highest among those, right? In accuracy from linear SVM, we go over 80%. So it's a nice step up. And if we do the normal data augmentation, so the translation rotation, in addition to just throwing in the data, we go to 82%. We see also a nice increase in precision and recall of the data. That was quite nice. But what we then also said, well, if we've got an LVOT case, and so that was characterized or classified as LVOT, and the other one was classified correctly as a good quality image, we can go back, as Daniel explained earlier, to see how did that happen. So we can propagate back and look basically at the attention maps. And the way that's quite nice to do that, I'll show you both at the same time, actually. So if a cardiologist or a radiologist would look at those data, this is where they would look, is LVOT present or not? You see that's where it's lighting up. And if you want to check is it's not present, you actually would look at the separation between the chambers of the heart. So I thought that was quite nice. We do all use deep learning as little Lego blocks, but it's quite nice to actually make the Lego blocks sometimes transparent and look a little bit inside and see why did this happen. So these attention maps are quite useful. I think also to convince cardiologists to accept this work, because they think this is all black, dark magic, which it is for us as well, it's at points, right? But if you then can look a bit under the hood, then you can actually make it a bit more explainable to them. The other thing we looked at was emotion-related artifacts. So there we looked at mistriggering. So if you acquire cardiac MRI, you do ECG triggering, and you don't, as Daniel also explained before, you don't acquire one cardiac phase in one go. You acquire several cardiac phases, but just one line of K space for each phase, and you do that over different thresholds. So you accumulate lines of K space over time, and then you try to sort them at the right place. So on top you see a good quality image. You've got to zoom in. It's a nice scenic cardiac short axis scan, and the bottom you see a blurry one where you actually kind of project through several cardiac phases at the same time because the trigger was wrong. So you had mixed lines of K space there accidentally because it was mistriggered. So again, we looked at the beautiful UK biobank, and the beauty is the curse. So we had almost 3,500 subjects there, of which 105 had this kind of artifacts. These are not patients. These are people who can hold their breath quite well and where there is not much mistriggering. Yeah, so it was a bit annoying because we still did not have a lot of training data. And rather than saying, okay, let's pick 105 with these motion artifacts and 105 which are healthy, we say, okay, we have to do something about this class imbalance problem. Let's actually generate, because we know how this artifact happens. We know exactly how that happens in K-space. So we can very nicely just simulate it. We take some good quality images and make them look bad. That's easy. Yeah. So we do this straight in K-space. So we've got, say, frame I, temporal frame I. We've got a K-space, temporal frame J. We've got a K-space, temporal frame N. We've got a K-space. But we can generate then a corrupted K-space by just, rather than sampling from the actual frame I, we sample from a frame I plus J. Yeah, we can just give it a regular offset. So here I'm just taking a line always every third one and just mix it up a little. And then I just do the inverse Fourier transform, go back to the spatial domain and get a corrupted image. Yeah, there are millions, infinite numbers of ways of how you could mix this. This uses Cartesian sampling. It's also important to know that this is not radially sampled data. It's also important to know that with UK Biobank, we do not have the actual magnitude and phase images. We do not have the K-space. But the Fourier transform, or inverse Fourier transform, is good enough for our purposes. We could go one step back and estimate magnitude and phase, but we haven't done that here. So what we do then is we can degrade images. We take a lot of beautiful images, and we've got 3,300, I think, good quality images if we wanted to, and degrade them. We can degrade them by various ways. We can mix every second line of k-space, or every 10th line of k-space, or every 100th line of k-space. We can mix different temporal frames into one temporal frame, or just always use the next one or something. So it's just zillions of possibilities. So we can I'm very proud to say we can make good data look really bad, right? And we can compare it to actual good quality and actual motion corrupted data. So there is a good quality data set here, the one I've shown you before, and here's a real motion corrupted one, and here's one where we've taken this one and just degraded it and get this one. And it looks fairly realistic. It may not be what would have happened to that patient if this triggering had occurred, but it's actually close enough for our purposes. So again, we just throw it in a slightly deeper network. This time we use a 3D convolution neural network, but actually, again, it's a 2D plus time network. So we throw the CNS sequence in, which is either a good sequence, one of our good sequences, or it's one which has been gradually corrupted. We also have, of course, the bad cases, which we can test or throw in. And we can do extra data augmentation as well, just rotation, translation, and so on. And then the output, again, is binary. Is it good or is it bad? Yeah, it's very simple. So we again compared it against the classic machine learning techniques, and you see actually that SVM is really good, 96% accuracy here. And if you just use a simple CNN with no augmentation whatsoever, just 105 bad cases and a couple of good cases, you just about get the same. But if you start doing just a normal translation augmentation, not even rotation here, you get a little bit higher. If you just do k-space augmentation, it's almost the same, but if you put the two together, you get to 98% of accuracy. The real difference, however, you see in precision recall on the F1 score here. Most of these guys are performing quite poorly here, and we get some really decent results here. So we can actually identify quite reliably ECG mistriggering in our databases. But then we want to go the other way around, of course. We want to take real bad cases and see, can we recover the motion? Can we do something about that? And they were inspired by a method which was recently stirring up a little bit in Nature. It's called AutoMap by Zhu. It was published earlier this year, where they did an alternative to compressed sensing. So a bit like what we heard in the first talk today, you have an undersampled k-space, and rather than doing compressed sensing, which is a dictionary learning approach, or doing something more clever, as we've heard before, they put something through this network. And the interesting bit about this, they do this now in k-space. So they start from the k-space, basically the spatial frequency domain, and then they have a fully connected layer times 2. Basically, it's a complex layer. It has imaginary and real components. And then they do some downsampling, and then they go backwards, and they estimate the reconstruction, which seems a bit silly because he knows the inverse Fourier transform. But the idea was indeed, if you train that on enough data, and you have an undersampled k-space, you can still reconstruct a nice image. The drawback about this technique, as which we have not solved this, is you can do this only in 2D. You can't put something 3D in here. This would be explosive. It is already explosive in 2D because it's a fully connected layer there. So we adopted this one and said, well, rather than working from undersampled data and having a nice super resolution output again, or a nice one which doesn't fall into the pitfalls of not violating the Nyquist theorem, we said we can motion corrupt our k-space as we did before. We can introduce motion there, and then we get a motion decorrupted restored image out. Basically, it's also a reconstruction from. So we start from k-space where we previously did simulations, and here we undo basically those motion artifacts in the same network. We did that almost. We did a bit of an add-on. So this is exactly the same method, but only that our input now is a corrupted complex k-space. So rather than undersampled, we switched lines of k-space here. And the output is some sort of artifact-corrected, reconstructed image, but then we did do a bit of a GAN approach. We treat this as a generator, and we have an additional discriminator with real images, and we get some nicer results then. We're still fiddling around with that. It was just really presented on Sunday at the construction workshop. So we used 75,000 2D images for training and 2,500 for testing. We, of course, tested it against the inverse Fourier transform, which we expected to perform poorly. We tried just the standard automap kind of approach and our proposed approach. And we get a slightly lower error than all the other approaches, slightly higher PSNR, and still slightly lower structure similarity index measure than the inverse Fourier transform. But that's because I think this method introduces blurring a little bit. And the result, as you'll see in a moment, they look indeed a bit like nonlinear diffusion. So the Fourier transform preserves the high frequencies a little bit better in the data. And here's a real example. So we have a real case space of a motion corrupted image. This is not a simulation. This is a real corrupted case, and we reconstructed that. Easy motion reconstructed this, and this is the result. And you see that this blurring motion going through, basically, I think you're looking at several cardiac phases at the same time, just kind of averaged, has disappeared. But everything looks also a bit smoother. Now, again, you have to think of why you would do that. You wouldn't want to show a radiologist this image. They would hate it, right? They would really, really hate it, because it doesn't look like a real acquired image. It looks like a too regularized reconstruction. But if your ultimate goal would be to get a better segmentation out of that and better measures of ejection fraction at the right phase and so on, then I think you're just interested in the final number. So this is why we look more and more, while we do look at the individual building blocks, the individual Lego bricks, in the end we want to do this end-to-end optimization and just want a number out of it, or diagnosis or prediction or whatever. Okay, this was the first part. This was cardiac. Now we move to the fetus, and this kind of links a little bit to Ualit's Viva last week, which hopefully is recovered by now. Done a great job with your spotlight talk, by the way. So here we're looking at fetal imaging, but we look at fetal ultrasound, not fetal MRI, and just a little bit at MRI. And we use it for organ detection, for registration, for compounding, and for tracking. And I'll be really quite quick because I realize it's almost 5 o'clock. So here we want to basically do this kind of soft labeling that Daniel before said, where you don't want to segment organs by hand and label them, but you want to say, is there a head in, are there limbs in, is there a spine, and so on. So we hand labeled a lot of data sets. We have zillions of ultrasound. That's the beauty about ultrasound. This was just, I think, 10, 15 cases at most, but each of them have 10,000 images, right? That kind of order, not quite, but we've got basically these image level labels without a segmentation. We've got these ultrasound images, and we use a very simple CNN approach. I'm not even going into layers and things. But again, what we get out of this are these soft proposal maps. And those we can threshold and extract bounding boxes, and we can do that real time. We can scan a fetus, and on the workstation next to the ultrasound machine, we get labels out immediately. And here's just some of those maps. We include the placenta, the maternal organ, and not the fetal organ. And that actually, I'll show that this is a problem because the fetus moves with respect to the placenta, right? So it can pop up at different places with respect to the fetus. But I think this whole method could have real nice applications to find the fetal position, to estimate the pose, to actually look a bit deeper and segment the organs. So do a second step. So first you do the organ detection, then you do the organ segmentation step. Or you could use it maybe for image-guided navigation for interventions, fetal surgery. And here are just some results, just showing, this is just a comparison between two different neural networks. And you see a nice bounding box for the head. It's just that the head is easy, right? You find it, you just follow it. Thorax is more difficult because it's, you see it sometimes sideways. Abdomen is fairly good. Spine is quite pronounced, but you get from what observers would click a bit different. They would put a narrower bit in. I think the network actually looks for a little bit more surroundings there as well to decide whether it's one. You've got limbs, placenta, and we also have misclassifications. Of course we do. In fact, the worst one is the placenta, as I mentioned before. If you look at the precision recall graph. The best one, I think, is the head here. Head is easy, really. So we're moving away from the head, finally. The other thing we worked on, and which was presented by Rob Wright, I should have said the previous work was by Nicolas Toussaint. Rob Wright, he worked on image registration here. He was inspired by Jadaberg's and Zisserman's spatial transformers, which are just a way of solving registration using neural networks, which is beautiful. So basically, you spatially manipulate feature maps within CNNs. You learn invariance to translation, rotation, and scale, which is exactly what you want, because actually these are the ones you want to recover, and you can actually do more generic warping. So you've got these building blocks. You've got the localization network, which gives you just some transformation conditional for then the actual transformation, where you basically create a grid on which you want to sample, and then you've got a sampler at the end where you actually generate the output on. And they showed in their work that you can, on the MNIST data set, you can actually resolve rotations and scaling, for example, here quite nice. You can just really register, reorient data sets with that. What Rob did, he created a co-transformer network, which consists of two of those networks, one for ultrasound and one for MR. So we worked on motion reconstructed MRI, but similar to, it's the same method that Ualit was using in his PhD, by creating high-resolution MR volumes of the head. We move back to the head now, because it's rigid, it's nice. And then we linked the two together and simultaneously taking MR and ultrasound and registering them to the same atlas space. For that, we had to create an atlas first, which was the tedious bit. So quite often you don't hear how hard it is to actually generate the training data and all these neural network approaches. So that required a very painful, careful alignment of lots of data set into the same space, using mixture of standard registration, manual reorienting, some bootstrapping as well, so redoing things in between, and also having age-dependent templates from 21 to 29 weeks. And we had in total 166 reconstructed MRI volumes and with 3D ultrasound pairs. And then we did data augmentation. So basically, we taken instances out of the atlas, left them out of the atlas as well, and rotated them to different degrees, just very mild rotation translation to very, very big ones. And that actually is what's probably happening in real life. The really big rotation with normal registration methods really can't handle, not at all. And you compared against two methods, just vanilla normalized mutual information, which people use just for multimodal registration, which comes from Guy's Hospital originally, and block matching. So a very simple rigid registration method. And the other one he compared it just to annoy me, because this was my previous work with Matthias Heinrich on the discrete optimization method and self-similarity context, a local, kind of non-local means-based, almost feature-driven method, combined registration, which worked pretty well on the MNI byte data set, which is MR and ultrasound head images for surgery. And then especially, so you see our approach, it did not perform perfectly, but it went down to kind of 3 degrees misregistration, just compared to the atlas, and under voxel resolution translation errors. The others did quite well. This one from Matthias Hein did quite well if there was just a little bit of misregistration, but it started failing as soon as the misregistration, the applied simulation was higher. And normalized mutual information and block matching just really did not work very well. It just failed, and we tried a lot. And this is just a comparison using landmarks instead of the atlas-based as a ground truth. And here's just one case: reconstruct MR, ultrasound reoriented, so they are jointly reoriented, and then shown superimposed. Your own Veronika Zimmer, who after her PhD, I also examined her, in fact, started working with me last year. She is now working on multiple probe ultrasound, where you take 2 ultrasound probes, could be one ultrasound system, which allows you to do that, or could be 2 separate ultrasound systems, and put them basically in a probe holder, just 3D printing design, and acquiring coplanar images. Yes, this was designed in an angle that they are actually coplanar. You can still do something more complicated than that, but from the first design it worked, which was nice. And then she wanted to fuse these, basically getting a larger field of view, because you see if you scan a fetus at this age, you don't see the full head anymore. It's too big. So you only see part of the head at any one time, 20 weeks or so. And she tried two different things. One was a Cartesian interpolation, basically fusing those two in their overlap region and using just a Cartesian linear interpolation. And the other one is going back to my roots, going back to Daniel's roots, in fact, going back to B-splines and recognizing that this is actually a polar coordinate system we're working on and using that to sample the data and fuse the data. And here's the example of if you just overlay them like it is, using Cartesian interpolation. So projector is very generous, but it shouldn't be, because you actually should see quite a clear line here, right? This is where the two probes intersect, and you see it becomes darker as you go across. So Veronica is a fantastic mathematician. So she worked through basically the distance of the probe, the angulation of the probe, and from that derived measures of how she could weight the signal response from the two probes. And doing that, you get this. I'll just flick this around. Oops, sorry. Flick this around a few times, so you actually can appreciate. You get a really, really nice, without doing much, right? We're even only just starting on thinking now about clever fusion techniques and what else we could do. Yeah. And another postdoc of mine, Alberto Gomez, he did as a very simple registration method, no deep learning, yeah, by doing a very fast deformable registration, feature-based. And while you're scanning, basically this is real-time. It's a real-time stream of data coming in. Here you see the real-time data here. It paints a picture of the fetus in 3D. It really completes the fetal body on its own, so you can kind of see how it's progressing. You see also some red lines here. Those are the cases which did not work, the frames that didn't work from the volumes, which are then discarded. But it's a fairly fast stream of data coming, of 3D data. And it has, of course, a lower frame rate than 2D ultrasound. It's quick enough that while you scan, it actually can compound the whole volume of the fetus. And you see some examples of the 3 different probes and how they fit together. There's also an overlap between those, so we're also thinking of how we can do more clever fusion there. And then finally, Bishesh Kanal, who is a joint postdoc between King's and Imperial, and co-supervised by me only. He works on extracting then the surface of the fetus. So you see, we do different building blocks. We find organs, we find the whole fetal volume, and then once we've done that, we can start looking at surface extraction of the whole fetus. And he puts two things together. He puts a segmentation step, the residual 3D unit, again, nothing fancy, and SLAM, which is a method mostly developed by Andy Davison, I think, when he was at Oxford, which does a simultaneous localization and mapping, SLAM, which is a real-time surface reconstruction method. He just puts two things together. We quite often in medical imaging don't invent things. We steal things and merge them in a nice new way. Here's just the setup. You feed a network 3D ultrasound plus time, so it's a 4D input stream. You put it into the segmentation, at segmentations, 3D plus timeout. You create then a virtual camera, so it's really like a computer vision, almost computer graphics approach actually, from which you can create 2D plus time depth images, which you would do with Kinect or other things. Yeah, so we just simulate almost a Kinect camera here. And then from that we can extract the surface, but we can also track the probe. We know where the probe was when the image was acquired without having any navigators, optical tracking methods whatsoever. We looked at a very cooperative fetus, a phantom first, which doesn't move. So we've got some input volume examples, compound them, and get a nice reconstructed surface. And we also get the probe trajectory out, so actually see how you traversed across in this case, the phantom, not the mother, and how you actually found the whole fetus in the end. It has still holes, of course. We did not run it long enough. And then we looked at real data. So every Friday afternoon, we scanned lots of pregnant women, and we tried it out. Of course, these are uncooperative fetuses. They do move, thankfully, and there we focused on the head. We just looked at the rigid aspect of the compounding and reconstructing the surface and seeing the probe trajectory there as well. So I don't have a nice conclusion slide. I just want to say gracias. Thanks for having me. And lots of questions.
Hi, thanks for the nice overview. I have a question on the first part regarding the data quality. So once you spot bad quality data, what would be, I think there's still useful information, but sometimes you don't, what's the value of this data? Do you throw out and then your next step would be to only work with good quality databases?
Yeah.
Or do you think there's hope with these data still to be integrated in?
So right now we really just focus on good and bad. I think we can do it in a multi-task classification way. We can say how bad it is and at what point it's too bad to be further analyzed. That we actually really can't recover it, that the error would be, the uncertainty of the reconstruction would be too high. If it's really too bad, that's quite valuable information because we know we have to call in the patient and maybe the patient is still in the waiting room so we can call them back in. Yeah. So otherwise some patients travel 2 hours into London to have their scan and then the next waiting list is another 3 months down the road. So this would be helpful. So while we are acquiring, we can call them back in. If they're kind of still in a range where we could do something about them, so I've shown that you can maybe take out the motion and reconstruct the data motion-free, lesser motion data. That's also valuable because then we actually have rescued the data. We don't have to exclude it from studies, so we make more data available to the community. I mean, everything we do in UK Biobank, we have to feed back into UK Biobank, so it actually might help other people too. And then also you have to think of why you're acquiring the data. We don't want to create pretty images, right? We want to create data which is useful. So if we can still calculate, say, the ejection fraction, even though the data is quite corrupt because our networks are agnostic to the motion, they actually ignore it and just pretend it's good data and just give you some good results. That's also helpful. Or if you want to do a segmentation, we've seen the example before, one line of case space and you still get a segmentation of highly undersampled data. There could be also highly motion corrupted data. Maybe you're just interested then in the segmentation in the end.
So I'm interested in registration part. I saw one paper from Mikai this year about unsupervised, learning of registration from
MIT Cornell.
Voxelmorph.
Yeah.
Can you make any comment
Yeah,
on that?
yeah, I was quite excited when I saw that work. It started at CVPR. They had the first paper there, and now at MICA was the more elaborate version, thankfully. I think this is exactly what's happening now. We go a little bit, I thought it was quite funny looking at it because we go a bit back to the roots. We know, like with the spatial transformers, we need a transformation model. We need some sort of final interpolation, which we also can do in networks. And this was basically putting that together, also putting in a similarity function, basically the cost function, the loss function neural networks, but there I think they used, it was a single modal approach, if I remember, it was single modal registration, but you could put in mutual information or whatever you wanted as part of your loss functions. Might be quite slow, you want something quick, that's why people usually do something quick like cross entropy. But it started going back to how we normally do this, with the difference is these things, I can't remember now whether it went through some loops or whether it was a one-shot registration. I mean, these methods now actually potentially could do a real-time one-shot registration without an actual optimization, because the optimization is in the training step. It's no longer than in the application, right? Yes. And that's the nice thing about all deep learning approaches. We have fewer coffee breaks now, I noticed, but but they are probably in the training phase. Yeah, it's nice. Voila.
Hola, Julia. The thing is, this data augmentation, I think is one of the things that has surprised me more, because in the typical schemes that we've been using for atlases, etc., we didn't really have data augmentation. Like it was like, okay, we have this number of atlases, and well, we need to work with, and you see that this makes a huge influence on the quality measures, and the thing I saw one paper from one of your postdocs that they were using free-form deformations to to generate more virtual kind of cases and examples. Just apply very small displacements
That
and
wasn't
then.
from us, I think from Eindhoven. But yeah, okay.
And so what I asked this guy is like, okay, you are assuming that these small deformations, you are capturing normal variability between subjects, and there is nothing physiological in there.
Yeah.
So
I don't think that's from us. I mean, you have to tell me which
Okay.
one it is. I don't think it is.
Okay, okay.
Because I get.
it's in the actual segmentation challenge.
So, yeah, okay. Yeah, okay. Yeah, I understand now. Yeah, I think I criticized him for that. I realized that. I don't quite agree with that. I mean, but remember, we used to do PCAs. We used to do shape models a lot to capture breathing motion. I think that could be a nice thing to put in these approaches if you want to do a normal breathing motion into this, then the PCA over in using registration, whatever. And remember what we did to simulate disease.
Yeah,
These
exactly.
things might all be coming back, right?
Yeah, because I really would like to see how physiological modelers enter to this kind of
They
things.
start doing
And
it, yeah.
it's likely that it's going to destroy their field also. Like,
I had a long discussion with Leo Grady on that
because,
as well.
I mean, you start to see in Mikai people talking, using deep learning
Yeah.
as an optimization algorithm,
Yeah.
really,
Yeah.
and to estimate parameters of the models, and really replacing even CFD simulations. So you have a lot of training on simple geometry. You run simulations and you learn the relation between the geometry and the vector field. And then a new case comes and boom, you have the simulation done. I mean, I'm really looking forward to see the faces of the VPH people and the Fusion community.
This is recorded, Oscar.
Yeah. So forget the maths and all this, just run deep learning. It's going to be a lot of fun.
Yeah, it will be.
I guess I wanted to make two comments to what Oscar said. I think you have a good point, but for example, if you, let's say you're using a deep learning approach for segmentation, and you say, well, in the traditional, if I use atlas-based approaches, multi-atlas segmentation, I don't do data augmentation, correct? But I normally do an explicit registration step, correct? I basically deform my atlas to match the subject. And in these registration, let's say if I use a UNet for segmentation, I don't do that. I basically do a one. So basically, I think what you're replacing, or part of the data augmentation effectively help you with not having to do an explicit registration. And for example, I think the other thing is many of these, I mean, the sort of the latest multi-atlas segmentation approaches all used to be patch-based approaches, correct? And I think that's effectively doing exactly the same. You basically composing this from multiple different subjects because you don't have a liver shape which actually looks like the liver shape you have. So I think you're doing something which is not too dissimilar. And for example, for the registration, when I spoke to the person who was doing the voxel morph, he was saying, well, perhaps you can't really do registration completely with deep learning, but you can get very, very close to the final solution. And then you could do a sort of a bit of optimization.
This
and
is
I guess
what,
the same is
we
true.
do in that
And I guess the
example
same
I
is
showed
true with a CFD simulation, correct? Perhaps getting to the final solution the deep learning will get you very close, and then you probably need to adjust a bit, but you can probably get there much, much quicker than you used to be able to do.
Well, the other way around, the CFD simulation can give you really nice training data. Exactly, that's what you do then, yeah.
Now you're in trouble.
So now I will speak in the name of the VPH community.
There's a corridor here for a purpose, right?
No, I'm kidding. It's just a curiosity. First, thanks for the talk. It's curiosity. When you do, for example, there's this segmentation, so along the stream during the echography, so does it somehow require training of the medical doctor, or does it affect the way the medical doctor is doing the exploration?
So I didn't bring a picture. So our setup is they look at the ultrasound. They don't look at the workstation at the moment. So they scan whatever they think is right. The same with the scan plane detection. They scan. We tell them after, it's more like a feedback right now. when they fit the right scan plane, so we can compare the one they've frozen and the one we would have chosen. Yeah, but of course, originally the ones they've frozen as the best scan plane, and that was the one that was used for training in the work by Christian. But more and more, because we start putting things closer together, they also start looking at our workstation. Ideally, we would have it in the ultrasound, of course, so we're talking to Philips and other people and see whether they're interested. And it could be a great training tool for them at the end, because it could help them to, when they actually want to find the head, we could actually steer them towards. If you know the trajectory, for example, we can actually say, you're here in the fetus, you have to move this way. I mean, there could be, and then you can think about steering the ultrasound in some nice way as well.
Okay. Last chance, anyone? Oh, yeah.
Wow, I'm amazed.
Sorry, thank you for this nice presentation. So I think in the first case you compute some kind of attention map. So here you are doing soft attention. And what about applying progressive network in order to gradually eliminate the future maps and only to pass the block of futures that are really important for this case? I think that your method will improve considerably in this case.
That's probably in the future work section of Nico's paper.
Okay.
Absolutely, there's lots to do. There's plenty of room for improvement and for putting things together in other ways. We're working on one problem. This iFind project involves also Daniel and Bernhard Kainz from Imperial. We have, I don't know, 10 postdocs or something working on this. So everybody's working on a slightly different project. And that's just on the image analysis component of the project. We've got people working just on the clinical side there as well. So it's close collaboration with clinicians. They sometimes are just really interested in very simple things. They just sometimes just want the biometrics. They actually don't care about the ultrasound image. They want the circumference of the head. And that we can learn actually quite quickly. There's also some nice work from Daniel's lab on that you can actually just learn these ellipses, basically, the measurements. So yeah, there's lots of scope. Probabilistic networks would be really nice. Yeah.
Okay, and I think that regarding the last case, you show here the segmentation of the whole fetus in ultrasound, in 4D ultrasound. So I think that probably, I don't know, you can apply this model to study the fetus movement inside the mother and to analyze some brain disorders.
Yeah.
Because I think that some people is doing that in the field of when the baby is born and something like that. It's really very nice here.
There was a Mika poster on that actually, where they studied RGB images of the born neonate and tracked the motion. Yes, and you could potentially do that now already in utero. Yeah. Thank you.
Okay, thank you very much. I would like to thank Julia, but also all the other two speakers, and I want to join me in a round of applause for them.